Good morning to everyone. In today's video, we are going to see the reflection coefficient and voltage standing wave ratios. So here, to understanding the concept of voltage standing wave ratio, whatever the energy in your transmission lines, whether it is in voltage or current, it will be flown in form of waves. Okay, in form of waves. So here, this voltage standing wave ratio um, given for given for a transmission line which is loaded other than the characteristic impedance. Okay, other than the characteristic impedance. So already in our previous class we just seen if the load is if the transmission line is terminated with characteristic impedance, we call it as matched line. So other than this characteristic impedance, if you terminated the line, the waves in your transmission line get reflected back. That means some part of the energy, some part of your incident wave, it return back as a reflected wave. So the combination of this incident and reflected waves will form an standard waves. Okay, so here already we know the what is the voltage and current equations of your transmission line here. Okay, so by considering these equations at your load terminal, so already I mentioned, if I consider this is a transmission line, at the load end I am considering x equals to 0, where the source end x equals to minus L. So here I am assuming at the load end what will be the voltage and what will be the current. Okay, so these are the values. So when voltage at the load, voltage at the receiving end, current at the receiving end. Okay, so please assuming that the load is other than your characteristic impedance, that is here I am assuming it is then ZR, or you may consider it as ZR, no issue. And the characteristic impedance Z0 equals to input voltage to the input current, or negative of the output voltage to the output current. So this is, I am assuming the equation number 1, 2 and 3 here. So I am substituting equation number 3 in your equation number 1. So here to find out I1 from the third equation, I can write it as an VI by the Z0. So I1 equals to II equals, that is incident current, equals to VI by Z0. In a similar fashion, IR equals to minus VR divided by Z0. So this is the equation. So here Z0 is the common element. I just bring it out on the left hand side. So Z0 IR equals to VI minus VR. So this is the equation number 4. So this side, in the equation number 1 and 4, the the right hand side terms are VI and VR is in common. So divide first and fourth equations. This is the format I get. So VR divided by Z0 IR equals to VI plus VR divided by VI minus VR. So please make sure the capital R represents the load, okay, receiving end, and the small r represents the reflected values. Make sure that. Whereas the load impedance, ZR equals to VR divided by IR. So this term will be replaced with ZR. So the final expression will be ZR divided by Z0. So here I am just bringing it out, VI common. Okay, VI common. So 1 plus VR divided by VI, and here also 1 minus VR divided by VI. On both sides, VI will be cancelled over to each other. So the reflected voltage divided by incident voltage is nothing but my reflection coefficient. Okay, reflection coefficient K. So ZR divided by Z0 equals to, so I replace VR divided by VI with K. So already the introduction related to your coefficient I explained in previous video itself, because this is the basic point. That's why in the starting class itself I just go through the reflection coefficient. So reflection coefficient at any point is defined as the ratio of reflected component of voltage or current to the incident component of voltage or current. Okay, so this value will be given it as reflection coefficient K. So ZR divided by Z naught equals to 1 plus K divided by 1 minus K. So cross multiply these things and rearrange the elements. So when you rearrange the elements, so ZR minus ZRK equals to Z naught plus, so find out what will be your reflection coefficient K. K equals to ZR minus Z naught divided by ZR plus Z naught. Okay, so this is the reflection coefficients whose values will be varies from -1 to 1. Whereas coming to the voltage standing wave ratio, it is defined as the maximum voltage to the minimum voltage. So maximum voltage is nothing but Vmax, which is nothing but the summation of your incident voltage and reflected voltage, and minimum voltage is nothing but the difference of those two things. So here also again, by using your reflection coefficient, I just bring it out Vi common, so it will be 1 plus VR divided by Vi, which is nothing but replaced with your reflection coefficient K on numerator and denominator, both will be cancelled over. So standing wave ratio S equals to 1 plus 1 divided by K divided by 1 minus K. Okay, so this is in terms of voltages. Similarly, we can provide the same thing for the currents also. We say that there is an current standing wave ratio, which is in ratio nothing but maximum current to the minimum current. This standing wave ratio is in the value between 1 to infinity. Okay, because the modulus of K will be varies from -1 to 1, so modulus of value will always be positive. So if I am assuming it as in 0, okay, if it is assuming it as in 0, K stands for 0, the value stands from 1. And if I am assuming the maximum value as 1 for modulus of K, it will be infinity for S. So the S value varies from 1 to infinity. So that's the thing, reflection coefficient and standing wave ratio. Thank you.